What we know so far. Yeah. Yep.
We saw the two models of frequency in the first model and the second model of Nyquist and Channel. Why in the first model we use the fundamental frequency to calculate the data rate, and the second model we not use the fundamental frequency, we use the bandwidth multiplied by as the formula.
In both models they use bandwidth. In Nyquist and Shannon capacity.
And in the first one, that's the fundamental and harmonic frequency, you use only the fundamental frequency multiplied by 2.
Yes, when we went through the first example, then we did a calculation of the data rate given some frequency. But the frequency, the Nyquist principle is that the maximum. Let's go back to the slide. The maximum, that's a good point. There's a relationship between the bandwidth and the data rate. So when we did initial calculation, we saw that we looked at what happens if we have a signal which is like this, and we assume that, okay, this could be 2 bits, and if we have a particular frequency, then we can calculate the data rate, or the maximum data rate. It's more general than that. That is, that if we have normally if we have a signal, it occupies some bandwidth. If we plot the signal, that's a typical shape of a signal where we have some frequency, the center frequency, and some bandwidth. FC is the frequency of this signal, where C means the center frequency. Yeah. Yes, when we've looked at our signals, we just use, say, 2, 3, 4 components. But in general, or real practical signals may have a wide range of components. And generally, we'd, instead of draw them like this, our signal would be shifted to some particular center frequency. My voice, if it ranges from several hundred hertz up to 3 kilohertz, so that may be drawn like this. When we want to transmit that, we often need to modulate that signal and shift it to a different frequency. If I want to transmit my voice over this microphone system, which is using, say, 900 megahertz as a center frequency, then I will shift my voice, the system will shift my voice up to a different center frequency. So that modulation, which is what we're going to talk about, I think, in the next topic. So the center frequency can vary, as we'll see, anywhere within our spectrum.
Some type of data, we have to put the FC that's suitable for that data.
Yes. So my voice, the original data, has frequency from 0 up to 4 kilohertz. But if I want to send it across the across the microphone system, it transmits at, say, 900 megahertz, a different frequency of my voice. So we actually have to shift that analog data to a different center frequency. And the result is that we get some signal with a center frequency and some bandwidth. And Nyquist determines that the maximum data rate you can achieve depends upon the bandwidth, in this case. The way that we modulate the signal, that is, this is simply FC plus half B on 2, the bandwidth on 2, and this is FC minus bandwidth on 2. So the bandwidth is simply from here to here, which is B, or BW in here. And that determines the amount, the data rate that we can achieve.
And in the first you teach about the domain and the frequency domain. We use in this case, if I get the fundamental frequency will be FC minus B over 2.
So these are both plots in the frequency domain. We've talked about the fundamental frequency of a signal, which was, say, this one.
And when we calculate the maximum data rate, we use 2 multiply F fundamental. Why is different between them?
When we shift and modulate our signal, then it occupies a range of frequencies, in this case, and the bandwidth we have available will limit how fast we can send. So there's a relationship between if we have a particular frequency and how many components that we can have is determined by the bandwidth. So if we go back to that first example, we'll see that as we increase the bandwidth, we increase the data rate. That first example that we had this square wave, increasing the bandwidth increased the data rate. If you go back to some of those calculations, we said, okay, if the bandwidth was 2 megahertz and we increased that to 4 megahertz and kept everything else the same, the data rate went from, I think, 2 megabits per second up to 4 megabits per second. In practice, generally, as we have a higher frequency, we'll have more bandwidth available and we'll get higher data rate. If we have, using optical fibres, for example, where we transmit light and we can send light at the frequency of light we'll see in the subsequent slides, we have a much wider bandwidth available and therefore can transmit at a much higher data rate. So the Nyquist and also the Shannon capacity give us an upper limit of how fast we can send our data under different conditions. In this, in the conditions of no noise, and the other one in the condition of with noise.
We have when we have more bandwidth, it means that fundamental plus the harmonic harmonic 3 or 5 times will be high.
We have more bandwidth in that case.
Represent that the fundamental should be high too.
Yes. So if we shift our frequency up, we'll get more bandwidth in that case. So there's a relationship between the frequency, the bandwidth, and the data rate. So the bandwidth of the frequency are related. So here we consider the bandwidth of our signal and get our data rate. Yep. So we know something about the relationship between the bandwidth and the data rate. We know something about the signals which are transmitted. So we have our transmitter. Our basic model of our communication system has a transmitter, our receiver, and a transmission medium. The thing that connects the transmitter and receiver. So that's what we're going to talk about now. First, looking at the things that we're interested in as computer scientists, we're going to talk about what are the different options we have for the different media, and then we'll focus on both, or we'll focus first on wired and then on wireless media. The things we care about when we want to select different transmission media, the main concerns are the data rate and the distance that we can transmit. So our media is our link between transmitter and receiver. What technology do we use for that link? We generally want to maximise our data rate. We want to send data across this link. We'd like to choose a technology which allows us to send as fast as possible. And we'd often would like to maximise the distance, because if we want to connect across or within this campus, then we'd need to choose some media that will allow us to connect the possibly hundreds of metres between the different computers all within this campus. So we need to choose a particular media that will allow us to transmit our signals across that distance. If we want to transmit between here and the other campus, we need to choose some media that will allow us to transmit 12 or 15 kilometres. And if we cannot transmit that far, then we'll need to use amplifiers or repeaters. And we'd like to minimise the number of intermediate devices. It'd be better if I could have a direct link from my computer to every other computer in the world. Of course, that's not possible. But we'd like to generally have links that are as long as possible, as long as practically possible. That is, we'd like to choose some media that we can maximise the distance we can transmit our signals. What impacts upon the data rate and the distance? Bandwidth, we know. We've seen that there is a relationship between bandwidth and data rate. Transmission impairments, again, we saw as the noise increases, the data rate goes down. Noise is a transmission impairment. Another one is attenuation. Our signal, when we transmit it, gets weaker over distance. So attenuation impacts upon the distance. How much weaker does the signal get over distance? We need to know that. And how weak of a signal can a receiver understand? So this topic will look at some relationships between how does a signal degrade across distance. Interference, also related to transmission impairments. If there's other transmitters transmitting at the same time, they may interfere with our signal. And in effect, we can treat that as noise. And we know that increased noise leads to lower data rate. Increased interference can lead to lower data rate. In some cases, the number of receivers available in or connected to some transmission media impacts upon the distance and the data rate. If you add more receivers in some systems, the distance at which you can transmit reduces, and so does the data rate. So see, these are some of the main factors that will limit the data rate and distance. This is something that we've spoke about bandwidth, frequency and spectrum. This is a diagram of the electromagnetic spectrum used for communications. So first, how do we read it? It's showing frequency. The numbers along the top are frequency given in hertz. So ranging from 100 hertz up to, what's this, 1 gigahertz, 10 to the power of 9, terahertz, petahertz. So from very low frequency up to extremely high frequency, this is the portion of the spectrum that we can use for communications. So when we transmit our signals, they are somewhere in this range of a spectrum. And what we see on here is some examples. So some of the things that we know, this is the visible light portion of the spectrum. So the light that we see is transmitted in this range of frequencies. Note that this is a logarithmic scale, which means that the bandwidth available in this part of the diagram is 10 times larger than the bandwidth available in this part. So in fact, there's a lot of bandwidth available in visible light. Even though it looks like it's only one small part, this is much larger in terms of frequencies available, or bandwidth, than here, and especially down here. We have infrared frequencies. So the things you use to control your TV at home transmits a signal using frequencies in this range. as do other systems. Microwave for TV transmission and different wireless transmission, say between towers for distributing TV and telephone calls across a country. The radio range of frequencies, we'll talk about that when we look at the wireless topics. And frequencies used by telephones. So our telephones basically carry frequencies which match our voice, so several hundred hertz to several kilohertz here, and power transmission systems transmitting electricity. And some of the technologies that we know about: AM radio, FM radio. When you tune in to a particular radio channel, what's the frequency? Anyone know a frequency of a radio channel, FM radio channel? 88. What was it? 88 megahertz. 88.1.
Actually, it can receive 84.5, but it's okay.
Let's start with this example. 88.1. This will say that this is the center frequency of that channel. Okay, so each FM radio channel occupies some bandwidth. This one centered around 88.1 megahertz. So in this diagram, where are we? This is 1 megahertz, this is 10, this is 100 megahertz. This line, 10 to the power of 8, is 100 megahertz. So it's around this area, FM radio. So if we draw the signal for that radio channel, not to scale, this is the center frequency, say 88.1 megahertz. If this is the frequency in megahertz. And each channel occupies some bandwidth. So in fact, the signal, as we know, contains a range of frequency components. And the minimum here and the maximum here. And that's our bandwidth of that signal. Now, I don't recall what the bandwidth of FM radio channels is. Let's say it ranges from 87.1 up to 89.1 to make the calculations easy. That is, it has a bandwidth of 2 megahertz. So when you listen to this radio channel, the transmitter, some tower, is transmitting signals with this range of frequencies, centered along here, but actually containing frequency components from 87.1 up to 89.1. So, but most of the energy, remember this diagram indicates the peak amplitude. That is, the signal strength is strongest for these frequency components. As we get down to here, it's quite weak. And in fact, in practice, it may be very low here, not zero. But the signal energy is concentrated in this area. That's why we say this is the real bandwidth of the system. Even though there may be some very weak signal coming out of the transmitter, we don't consider that. So this is the signal for our radio channel. What you do is you tune in and you listen to this, you tune into this frequency, and the next radio channel, if we draw it, would have some separation, and whatever the value is here, 92.3. The next radio channel on the spectrum would have a similar signal, but at a different center frequency, representing a different channel. So all the FM radio channels occupy some portion of the spectrum around this area, around the 100 megahertz, plus or minus several tens of megahertz. So similar with AM radio and TV, that's a similar arrangement.
same bandwidth as
or can intermodulate?
First question, does it have to be the same bandwidth? Normally, say FM radio channels, you need a license to transmit. Okay, you cannot go and create your own radio channel and build a tower and transmit, because you'll interfere with others potentially. And normally your license allocates you a particular bandwidth. So normally most channels would use the same bandwidth. They don't have to, but for FM radio you only need a particular bandwidth to transmit the music and the voice at a reasonable quality. So normally, yes, they would be the same bandwidth, but they don't have to be. AM radio would have a different bandwidth, much smaller. TV has a higher bandwidth, so they don't have to be the same bandwidth, but typically FM radio channels would be allocated the same bandwidth as each other in different portions of the spectrum, and they should be separated by a distance such that they don't interfere with each other. Because, so that's this portion here. In practice, it's not as simple as this. The signal gets weaker. It's not quite zero here. It's quite low, but it's not zero. So there's some separation between the channels such that even if the signal is not zero, but it's very weak, it will not cause any noise or interference with this other channel. When your receiver is tuned in to listen to this channel, it's receiving this signal plus any of the small leftover signal from this channel, because it may not be down to zero yet. But because this one is the strongest, we can receive and understand what this signal is. So even if there's a small amount of energy coming from this transmitter, we can still, this one's much stronger than this. So we consider this noise, and this is the signal strength. If the signal strength of what we want to receive is much larger than the noise, we can successfully receive. And the Shannon capacity shows that relationship. And that applies not just for FM radio, for most transmission systems. We have a particular centre frequency, we have some bandwidth, and we have some separation into channels where licenses are used to allocate different organisations channels. And that's why bandwidth has some cost associated with it. Because there's only a limited amount of spectrum and there's a high demand for it, then people have to pay for a license. And therefore, the more bandwidth that you want, the more you need to pay, the larger the cost. So generally we'd like to choose signals which occupy a small amount of bandwidth to reduce the cost of our transmission system. It's cheaper to buy an AM radio channel than an FM radio channel because of the bandwidth. So these are examples really of wireless transmission systems, similar with satellite. So the satellite TV and even satellite internet systems transmit in frequencies in this range of gigahertz. So those satellites have licensed to transmit on particular frequencies. And there are organisations, both nationally and internationally, that divide the spectrum into the different uses. Some portion of the spectrum is reserved for AM radio, other portion for FM, and so on. So all of the spectrum is in fact divided into particular uses, and you need to get a license to use those frequencies. There are some special cases, some parts which are considered unlicensed, which means the user doesn't have to go out and get a special license to use it. Your wireless LAN, do you have a license to transmit from your laptop? I don't think you have a piece of paper saying you can transmit. That's in what's called an unlicensed band. Wireless LAN has a centre frequency of around 2.4 gigahertz. This is portion of the unlicensed band where there's some bandwidth allocated for specific applications, and one of them is for wireless LAN transmission. So the individual users don't have to pay for a license. anyone can transmit at 2.4 gigahertz. Within there are some rules as to what you can transmit.
Free for everyone.
Free for everyone, unlicensed. Yeah. But the problem with that is that because it's free for everyone, anyone can transmit. As a result, you can get interference. I can be transmitting on one frequency, you can transmit on the same frequency. The receivers will hear both transmissions and may not be able to understand what was transmitted. So, of course, it's free, but it means anyone can use it, and you start to get more interference, and the quality goes down. That's why different technologies have particular rules. We will not cover it in this topic or in this course even, but wireless LAN has particular rules to try to avoid that interference.
Is there unlicensed bandwidth for FM radio?
Unlicensed band for FM radio, there's...
I think there's 108 megahertz, but I use it to do a single radio and use it frequency.
I don't know what the frequency would be. There are different types of licenses. There's amateur radio operators, so there's frequencies allocated for amateur radio where you can transmit from your home and so on that particular frequency, which is not in the 2.4 gigahertz. It's still licensed. You need to sit an exam to get that. Yeah. Yeah. So I think it's still licensed. Yeah, but there are different rules as to who can transmit. Yeah. So amateur radio is still licensed.
And we have the
CB radio.
is unlicensed.
Yes, so anyone can use that. So a particular portion of the spectrum is allocated for those walkie-talkie CB radios. So the organisation, and there's a link on the website which points to how it's all split up into the details. It's done both on a national level and an international level. So internationally, they break the spectrum into different applications. So some portion of the spectrum is reserved for FM radio, some for AM, and so on. And that's common across the globe. But it's within those portions, within each nation, it may be separated even further. And it may be modified a little bit. But most countries would use the same division of which frequencies for FM, which for TV, and so on. But there are some variations in different nations. There's a link on the website that shows a more detailed picture of that, which is the division, and you'll see, I think it's for the US-based frequency allocation. I think there is a Thai one somewhere as well. I'm not sure if it's on the website. So, we have this amount of spectrum, or this portion of the spectrum that we have available to transmit our signals. The other examples we see here, and what we're going to go through, is some of the wired transmission systems, which is the same principle. Twisted pair, we'll see we can transmit electrical signals up to a range of about 100 megahertz, 10 to the power of 8, or a bandwidth of about 100 megahertz. In fact, some even go up to 250, even 500 megahertz. Coaxial cable is another system with a slightly higher bandwidth. We see the bandwidth is the minimum frequency up to the maximum frequency. Even though this looks bigger than this, be careful. Because of the logarithmic scale, it may not be. This goes from 1000 hertz up to almost 1 gigahertz. So the bandwidth is almost 1 gigahertz. This goes from 0 up to 100 megahertz, so the bandwidth is only 100 megahertz. So even though the line is longer, the bandwidth is less. Similar for optical fibre. We'll talk about what that is. It has a very high bandwidth available to use. 10 to the 4 up to 10 to the power of 5. Which is much higher than those other systems in terms of bandwidth. We're going to talk about those three technologies as examples of guided or wired media. Twisted pair, coaxial cable, and optical fibre. And then we'll go through different aspects of wireless transmission. First, let's talk about using So we're using wired media, sending electricity across cables, using electrical cables. We transmit some electrical signal across some conductor, some conducting material. Let's say copper. Copper wires are a good example of a conducting material where we send electrical signals across it. And this is a common example of what's used for wired transmission. When we do this, if we transmit our electrical signal across our conductor, then when we transmit that signal, that radiates energy out. And it also can pick up energy from other sources. So if we're transmitting across one wire, some of the energy goes out of that wire. And if there's nearby wires transmitting, then energy from them may be picked up from our wire. What that means is we get interference. When we're transmitting an electrical signal across our wire, we can have our signal interfered by other sources of energy. Not just other transmissions, not just other data transmissions, but any electrical system, some power generator, for example. So our transmission can cause interference on other cables, and other sources can cause interference on our cable. Interference means poor signal quality at the receiver. That is, we're transmitting our signal, plus there's other, effectively, noise on the system. We know that the increased noise, our signal quality goes down. So we'd like to minimise the impact of interference. How do we do that? Well, there's different ways. We keep our cable short, is one way. We'll show you some examples. So if we've got our cable, then we're sending inside, there are some wires, copper wires, and we transmit our signal across those wires. The first problem is that some of that energy radiates out and can interfere with other transmissions. And similar, we can pick up energy which is coming from other transmissions. And that causes the interference. Keep the cable short can minimise the amount of interference, but that's against our goal of increasing the distance. We said in the first or second slide we want to maximise the distance. Of course, we'd like to minimise interference by keeping the cables away from other sources. Don't put your transmission cable near any electrical sources. Well, that's not easy in practice, because wherever you want to put the cables, there are other transmissions. So that's not very easy in some cases. So the other way is to design the cables so that they minimise the amount of energy they radiate and that they pick up. So use materials to shield them from interference. Give some coating to the wires so that other transmissions will not go through that coating. They provide some shielding from interference. Organise the wires so that they don't interfere with each other and others. And that's what we'll see in the next slide. So that's common for the next two examples of wired media. Twisted pair refers to this type of link, or wired media, where we have a pair of copper wires and they are wrapped around each other in some spiral pattern. The reason for wrapping them around, for twisting them around each other, is to minimise the impact of interference. If you twist them around each other, then even if there is some interference, it turns out the receiver can remove that interference so that it has a limited impact on our signal transmitter. So twisted pair refers to twisting a pair of copper wires around each other. These are the most common and probably least expensive communications media that we use today. It's used in telephone networks. So your link from your telephone into the wall, into the socket, is using a twisted pair. And often from that socket out to the telephone exchange, maybe also using a twisted pair. And in the old times, the links between telephone exchanges across a country were using twisted pair, but nowadays they're upgraded to optical fibre in most cases. So telephone networks and almost all in-building networks. our telephone lines in this building and our computer network in this building is using twisted pair. Yeah, twist because it minimises the impact of interference. Yeah, the noise on those wires. Pass them around. They are just two endpoints from one of these cables, the normal cables you plug into your computer. Pass them around. What you'll see is that, and there are some others, you can still see the endpoints here, don't pull them off. You'll see that there are in fact 4 twisted pairs. So each LAN cable has 4 twisted pairs. You can see that they're colour coded. There's a white one and a colour wire. Each of those individual wires is simply a copper wire with some shielding or coating on it. In our normal Ethernet communications, how fast do we send across these cables? What's our data rate? When you connect your LAN, your computer to an ADSL modem, what's the data rate you can achieve? No, I can get faster than that. You plug this into your computer and plug it into the wall or where the other endpoint, how fast can you send? How many? 100 megabits per second. That's the typical speed. Most computers have a LAN card that can transmit at 100 megabits per second across these cables. And in fact, so this is using what's called Ethernet, a technology for LAN communications. And this is full duplex. We can send 100 megabits per second in one direction and at the same time receive 100 megabits per second in the other direction. And the way that it works is that they transmit on 2 of the pairs here. We have 4 pairs, 4 twisted pairs. Ethernet uses 2 of those, transmitting on one, receiving on the other, sending a signal on one pair of wires and receiving on the other pair. So it only uses 2 of the 4 pairs. If you've got a gigabit Ethernet card, we can send 1,000 megabits per second. To transmit at that speed, it actually just uses 4 pairs, or 4 pairs. So most computers nowadays have a LAN interface that supports both 100 and 1,000 megabits per second. It depends whether the device you're connecting to supports both. If so, you'll transmit at 1 gigabit per second. And that uses the same cable, but uses all 4 pairs rather than just 2 pairs. When you're using the normal 100 megabits per second, 2 of the pairs are wasted or are not used. So that's...
So it's not like 2 from 100 and 2 from 100 and combined become 200?
No, it's also the speed of 100 is not just to do with the cable, it's to do with the device that's transmitting, your transmitter and the receiver. So these cables can be used for both of them. So, all right, so the next thing we say that, okay, there are different types of cables, twisted pair, different qualities. First, we can add shielding or not provide any shielding. Now, shielding shields the wires and shields your signal from interference. The less interference, the faster you can send, the higher the signal quality. So shielded twisted pair allows for higher data rates or better quality signals. Unshielded twisted pair, lower data rates, lower quality signals. What is this, shielded or unshielded? Unshielded. This is called unshielded twisted pair. All right, there is some outer coatings and so on. Shielded twisted pair has more coatings around the individual pairs to shield them from interference. The practical difference is that this one we can bend. Shielded twisted pair, the coating makes it much more rigid, much harder. So it's much harder to bend shielded twisted pair. So shielding can give us better quality signals, but in practice it becomes hard to deploy. To then put cables along the floor and up through the ceilings and install them, if they do not bend very well, they're very hard to install. So the most common form of twisted pair is unshielded twisted pair. That's what these are. Within them, there are different quality levels or different categories. So you'll hear about things like Category 5, Cat 5, Category 6. So the normal, and it even says on some of these, this is verified to Category 5. It says on here that this is a Category 5 wire. So it's to do with the quality of the wiring and the shielding, or the quality of the copper wires inside those twisted pairs.
And I guess it's more expensive.
And it's more expensive. The higher the quality, the more expensive the cable. Yeah. And higher, or Category 6, because it has higher quality wires, generally can allow larger bandwidths to be transmitted. And I think the typical bandwidth for Category 5 is 100 megahertz. So a signal being transmitted across these copper wires has a bandwidth of 100 megahertz. Category 6, which provides higher quality wiring, supports normally up to 250 megahertz. Maybe higher in some cases. So with a larger bandwidth, we can send better quality signals, higher data rate. So there's some difference in the types of cables.
And Cat 5 100 megahertz, so the maximum data rate should be 200.
Remember, there's not an easy relationship between here and here. If we look at our Shannon and Nyquist capacity, it's not simply double. It depends on the signals we were sending across that. Yeah. Yeah. Depends on the noise in the system. And also, the design of the systems, one factor is that we know that the signal gets weaker, and it depends upon the transmission media of how much the signal gets weaker. So most technologies would have some limited length. You cannot use a cable longer than 100 meters, is the typical length. Because the design of the cable, there is always some interference. If you're greater than 100 meters, the amount of noise that comes onto the cable will be too large, such that the receiver will not be able to distinguish what it receives. Whether when it receives a signal, it's a combination of the transmitted signal and noise. So if we're longer than 100 meters, the receiver will not be able to understand what the transmitted signal was. So usually there's some limit or recommended limit on the maximum length of your cabling. There are other reasons for this limit in Ethernet as well. So that's one example, and the most common transmission media used for wired communications, twisted pair. Another example that you may have seen or used is coaxial cable. Here we have two conductors. Instead of wrapping them around, twisting them around to avoid interference, they are arranged in a way, and another way to avoid interference. You have one conductor, some insulation, and then an outer conductor around it. So this is a cut cross-section of our cable. So we have two conductors, one inside the other. And it turns out this is another way to avoid interference. Coaxial is that they're on the same axis, those two conductors. So this is commonly used in cable TV systems. If you've got, in the past at least, cable TV to your home, often those systems use coaxial cable. Also used in some audio and video cabling. So connecting components together in an audio system can use coaxial cable. Some long-distance telecommunications used coaxial cable, but generally being replaced by optical fibre now. So long distance we mean between cities, between countries. It provides more shielding compared to twisted pair. So more shielding means that we can send signals and they can be understood easier at the receiver, so we can get higher data rates. We can have more devices on a shared line, and we can cover longer distances compared to twisted pair. A typical topology of a cable TV network may be that we have several homes in some neighbourhood or on a street. So we have the different houses or homes on some street, and the cable TV network, the operator who provides you cable TV, has a single cable running along that street using coaxial cable, and you connect into that cable. And in fact, it comes back via coaxial cable and maybe some other technologies to the TV station. That's a very simplification of the cable TV network. TV station transmits the signal on this coaxial cable, and it's received by all of these homes, the same signal. Because with TV, what you do is transmit a signal. This is the frequency domain plot. Where this represents one channel, this is the signal transmitted. It's actually a combination of the signal representing 3 different TV stations, 3 different channels. So we transmit this signal along here. Everyone receives it, receives the content from all 3 channels, but just tunes into one of them. When you, on your remote control, choose channel 5, then even though you're receiving this entire signal, only this portion will be sent to your TV, or we use to display content on your screen. So the entire range of channels are transmitted across that coaxial cable.
Send all the channels in the one cable.
Yeah. Yeah, so the TV station sends all TV channels at once, the one transmission. It's just that your TV tunes into just one of those channels and uses that to display the content on your screen. So in fact, you're receiving all of them at once, or a signal representing all of them at once. So we transmit that signal across the line. The more houses you connect to this line, the lower the signal quality generally. So there's a limit as to the number of houses that can be connected to that line. If you have more houses, then the signal slightly degrades as it goes past each home. So it gets weaker and weaker, so we can have a limit. So where we say that we can have more devices on a shared line, here's a line that's shared amongst multiple users. Compared to twisted pair, we could have more houses on that shared line than if we were using twisted pair.
When we have the booster, we call that amplifier. Is it an analog signal sending on?
Yeah, this is an analog signal being sent.
We use amplifier.
So we can, if we can have a booster that, or an amplifier to increase that signal at different points. When compared to the twisted pair, so compared to twisted pair, because it provides more shielding, it can provide us higher data rates, and as a result, more devices on the same line. We can share that line amongst more devices and more users, and in fact also longer distances. So from those perspectives, this is better than twisted pair.
And compared with the shield with pair, we have shield too.
Yeah.
This one is still better.
Still, I think coaxial cable provides a much larger bandwidth. We saw on the frequency spectrum it provided up to 1 gigahertz, a bandwidth of 1 gigahertz. So we can still get faster on coaxial cable. But there are other factors. Cost comes into play. This is slightly more expensive, especially for in-building and small area networks. So even though we can get faster, do we need faster than 1 gigabit per second from my computer to this computer? Most likely a hard drive will not be able to generate content fast enough to be able to send that. So there's a cost involved of using different technologies, so that's why twisted pair is still commonly used. It's much cheaper, even though it doesn't provide these higher data rates and longer distances. For the purposes we need it for, it's suitable. So it's not used so much in local area networks or even wide area data networks. The next and the last example for wired technology is optical fibre. This is not sending electrical signals, this is sending light. So what we have is some very thin fibre of glass or plastic, and we have a light emitting diode at the end, some laser, and we send light and it reflects through that fibre until it's received at the other endpoint. The light is the signal in this case. And we have some shielding and some cladding outside that fibre to protect it. And in fact, most cables will have, similar to these, have multiple wires inside. Most optical fibre cables will have many fibres inside. So the fibres are very small and they are many inside a single cable. Yes, so we have one bundle or one cable, we're going to have many fibres inside it.
Each fiber one bandwidth.
Each
fiber transmit one bandwidth.
So the basic is we think we send one signal across each fibre, but in fact you can send multiple different frequency signals across the same fibre in some cases. So you can send...
The core is one fiber.
Yeah, this is one fibre here.
One fiber.
Oh, well, let's say this is one fibre and that's put inside a cable with multiple of these. But this is actually the fibre here. This is just some cladding or some protection on the outside. Yeah. Same as if you look at these, the wire is actually inside these coloured parts. The copper wire, the conductor. Outside is just some plastic shielding or protection of that wire. That's not a wire. Yeah. Yeah, it transmits light frequencies. So anything that can generate light can send it and onto that optical fibre. Yep. So optical fibre is used in long distance communications. Some of the characteristics it has: the amount of signal that is lost over distance is much less than using these electrical cables, the copper conductors. Therefore, we can transfer across larger distances. We can have a much larger distance before we need an amplifier or repeater. A single fibre allows transmissions at much higher bandwidth than our two previous systems, and therefore we can have much higher data rates. Tens to hundreds of megabits or hundreds of times larger than a single electrical cable. So much faster. Generally, for the same amount of data rate, they're much smaller in size, the cabling, and lighter in weight. And that's very useful when deploying them through buildings and so on. Rather than having to use a large group of electrical cables to connect between two cities, you can have a much smaller cabling system using optical fibre. And interference from other sources is not so significant on optical fibre. So you can place them near other electrical sources and interference is not a problem. Whereas if you place a lot of these electrical cables near a big source that generates a lot of power, that could interfere with our signals. So they're used in long distance communications where we need to transmit a large bandwidth or a lot of data, say between one city and another, because we need a cable to transmit the data from all the users in one city to all the users in the other city. In some, or in telephone networks, so connecting cities in telephone networks, in some local area networks, but not so many, and citywide networks. So you have a large company, or you're a telecommunications company which runs a network across Bangkok. You may have a network of optical fibres across the city to connect different sites together. So much higher data rate and longer distances. And I think the next slide summarises those three, puts the numbers to them. The first two, twisted pair and coaxial cable, approximately data rates around 1 gigabit per second. A little bit more depending on the particular technology, but we're talking in that range. Optical fibre, we're talking about hundreds of gigabits per second. So much larger bandwidth, much larger data rates. With distance, maximum around 2 kilometres for twisted pair, 10 kilometres for coaxial cable, optical fibre around 40 kilometres. So now if you want to connect from Japan to the west coast of the US, you need to go across the Pacific Ocean. So they need to lay some cables under the ocean, and every so often they'll need a device which is an amplifier or repeater. We want to minimise the number of them. So that's where optical fibre is useful. We can travel 40 kilometres and then have a repeater and then another 40 kilometres. And those repeaters cost money. If we're using one of these other technologies, we could only go 2 or 10 kilometres then have a repeater. So we need many more repeaters to cover a particular distance.
The optical cable is mainly send digital data.
Yes.
And not send analog.
It's an analog signal. We can send analog signals or digital signals, mainly used for digital signalling though. We can send any type of data, analog or digital data. We can send voice over optical fibre, but we'd need to do some mapping. Electrical cables for low data rates are generally cheaper, but because optical cables are the equipment, the transmission equipment, the repeaters are more expensive. To deal with the frequencies and to generate the signals, the equipment is more expensive. But if we want to transmit at a high data rate, well, what option do we have? We want to transmit at 1 terabit per second. We can use many electrical cables or one optical fibre. And that's when optical fibre becomes cost effective. When we have high data rates, it can be cheaper than using many electrical cables. Unshielded twisted pair is very easy to install, this stuff. And that's why it's very common for local area networks, where you and I need to install it. Shielded twisted pair coaxial cable is more rigid. It gives us better signal quality, but is harder to deal with. Optical fibres, if you cut them like this, we've cut these, we could easily join them together. It's quite easy to join them back together manually. You can do it by hand almost. And you've got the original cable. If you cut an optical fibre, you need very special equipment to join them back together. So it's much harder to install optical fibres. So there are some of the trade-offs that are involved. So they have different purposes. There's no one best technology in that case. The last two slides give us just a little bit of detail about the characteristics of those. It talks about the range of frequencies used. I think this should be 100 megahertz, not 1 megahertz. I think that's a mistake there. So the range of frequencies used by each. Different technology or different media have different physical characteristics, means the attenuation differs. This is some approximation of how much attenuation over distance. Remember, our signal gets weaker. It attenuates across distance. By how much? How much power do we lose across distance? We know that we can measure loss of power in terms of decibels. So here are some numbers. For example, 0.7 decibels per kilometre if we're transmitting at 1 kilohertz. So different characteristics in terms of how much power is lost. Signals have particular delay and typical spacing between repeaters, or maximum cable lengths given there. Well, attenuation is how much we lose. The signal attenuates, gets weaker. So this is saying, say, 7 decibels per kilometre. So the loss over 1 kilometre is 7 decibels. The gain is minus 7 decibels. Where? Terahertz. We're sending light. Light, if we go back to, I think, the third slide of that spectrum chart, it's from that lower range on that spectrum chart, which is around the order of terahertz, not hertz. Whereas these two can go from 0 up to the maximum value. This is in a particular range of the spectrum.
So the cable will light up when there's transmission?
Sorry?
The cable will light up when there's transmission?
The cable...
Light up because there's light transmission.
Well, yeah, we're sending light along some glass or plastic. So I guess if you could look in there, you would see that light. Colourful. All this shows, you can look at a later stage, it's not so important. It's just showing that how much the signal attenuates. Signals attenuate at different frequencies at different levels. So for our coaxial cable, for example, remember our signal has many frequency components. The components with a low frequency have less attenuation than at a high frequency. So our signal actually is made up of multiple components. Maybe the main point here is that this is the attenuation at different frequencies. Twisted pair at the higher frequencies of 1 megahertz has a lot of attenuation. Optical fibre at the maximum frequencies, similar level of attenuation. Coaxial cable, sorry, here. Optical fibre, and this is the range of frequencies it's using, it's much less attenuation compared to these two. And that's why we can cover larger distances with a single cable. The signal doesn't decrease as much as these two. Any questions about those three technologies? So what we've gone through is just 3 example technologies for wired media. There are others, but these are perhaps the most common that we may come across, especially twisted pair and optical fibre. Any questions before we move on to the next part? We've covered guided or wired media. The next thing is wireless. Both how does wireless transmission work and what are some examples of wireless media. But we've reached a point where we have time, so we've finished early and we'll have our quiz. We'll have our quiz now.